Alright, in this video I'm going to be talking about derivatives and integrals of vector-valued functions. So just to remind you what we were talking about last time with the vector-valued functions, this is a function that takes in a real number and gives you back a vector, right? So usually we're going to call this function r of t. R is going to be a function that takes in one real number and gives you back a vector. Now I'll just say, the dimension of that vector as yet undetermined, but we're mostly, especially today, and in this course, we're going to be primarily interested in plane curves and space curves, right? Curves that live in a plane and curves that can range freely in space. So I'll say that a vector-valued function that maps into R2 is going to be a plane curve. Okay, so R, which takes a real number and gives you back a two-dimensional vector, with R of t is given by some, x component function and some y component function. This is a plane curve. Okay, and in the same way, a space curve is going to be one that goes into R3. And it's going to have an x component function, a y component function, and a z component function. Okay. So that R of t is x of t, y of t, and z of t. This is a space curve. Okay. I think probably for the rest of this video I'm going to be talking pretty much exclusively about space curves. Okay, the first thing I want to tell you about is the derivative. Okay, and since these functions are taking in a real number, much like the functions that we studied last year, the derivative is going to it's going to work the same. It's just all that's different about this from AP Calculus is that the output is a vector. But we know that vectors in many ways work like real numbers, right? We can add them, subtract them, multiply them by a constant, divide them by a constant, things like that. So if I was to, tell you about the definition of the derivative of this function r of t, it probably wouldn't be surprising to you that it would be the limit of rise over run. It's just kind of a question of what does rise mean now, right? So I'm going to define the derivative of a function r. So for that r prime of t equals the limit as delta t goes to 0, the limit as run goes to 0 of rise over run. So what is rise? It's the difference in the dependent variable, the difference in the output. So that's going to be r of t plus delta t minus r of t. Okay. And then run is delta t. Now if we think about this, this actually this makes sense. This is a kind of a sensible expression because we can take the difference of two vectors, right? We can subtract two vectors from each other and that would give me back a vector, and I could divide a vector by a real number and that would still be a vector. And it would kind of make sense that the rate of change of a vector-valued function would be some sort of vector itself. And in the next video, you'll see kind of geometrically what does that look like and what happens when we start thinking about the vector r prime of t against the function itself. Okay. But for now, that's going to be the definition of the derivative. We're not going to actually work with the definition of the derivative in the same way that we did a little bit in AP Calculus to find derivatives. I'm just going to, assume that you would know how to do that if necessary. Because it would be the same, you just have to do it on each component. So I'll give you an example. In practice, we're going to take a derivative of a vector-valued function by taking the derivative of each of its components. Okay, so the example I was thinking was going to be cosine of 2t t e to the t, and what else? T to the. Okay, now, at this point, we're pretty new into multivariable calculus. We just spent a semester doing linear algebra. Probably very few of you are concurrently in my AP calculus. So it could be a while since you've taken the derivatives, right? And we were really good at this last year, but I don't know, maybe you've forgotten. So I'm going to start by just taking the derivative of each of the pieces. So basically the instructions would be something like find r prime of t. It's very, very easy, direct beginning question. Well, r prime is just going to be the derivative of x, the derivative of y, and the derivative of z put together into a vector. Okay, so when I take the derivative of cosine of a thing, that's negative sine of that same thing, maybe times the derivative of that thing. So it'll be negative 2 sine of 2t for the chain rule. This is a product, so I'm going to have to observe the product rule. I'm going to take the derivative of t with respect to t first, that's 1, and leave e to the t the same. Then I'm going to add in, leaving t the same, and taking the derivative of e to the t, which is just e to the t. And then the derivative of t to the 9 is going to be 9 times t to the 8. Okay? See, this is very doable for us. I don't think I'm going to need to do a whole bunch of examples of me taking the derivative of a vector valued function. There's going to be plenty of excitement with the derivatives of r of t, but that's yet to come. Okay? I think the next thing I need to tell you is kind of like the differentiability of a vector valued function. Now, in AP calculus, we were satisfied for this limit to just exist. That was going to mean the thing was differentiable. And if that limit didn't exist, well, that could maybe be evidence that we had, a vertical tangent, a sharp corner in the graph of the function, jump discontinuity. There was all sorts of reasons that limit could maybe not exist. But we're going to actually need a little bit more than that limit existing for a vector valued function. We're going to need for it to be, we aren't going to call it differentiable, we're going to call it smooth. In order for it to be a smooth curve, we're going to need not only for that derivative to exist, but we're going to need it to not equal 0. Okay, so a vector valued function r of t is what we would call smooth if r prime of t exists and r prime of t is not the 0 vector. And I'm realizing there are probably, there might be 1 or 2 people in this class now that did not take the linear algebra class. And when I say the 0 vector, I mean the vector that has just a bunch of zeros in it, like in space 0, 0, 0, origin. Okay, that's what I mean. Okay, so there will occasionally be the types of problems like, hey, here's a function. Give me the intervals on which this thing is smooth. And you will see over the course of the rest of our discussion why we would need this, why we would need a function to be smooth. Probably, in class, I will show you why, using some graphs, what would happen if the derivative goes 0, and what can happen is you can end up with a sharp corner. But, plenty of discussion on that still to come. So where is r of t smooth? Okay, for this one, this thing would be smooth everywhere, right? Because this thing is equaling, it exists everywhere. And the only time that this can equal 0 is at t equals 0. But at t equals 0, this is not 0. Okay, so then that means, right? I mean, this is 0 very frequently, but any time that this would be 0, we'd have some kind of pi over 2 type number, and then that's not going to make either of those 0. So let me give you the example that I'd cooked up that does have a point where it's not smooth. Let's see. Oh, well, I had one. I'll start off with I didn't stop to think that I would have an example already on the board, but I had one that was like 2, 1 minus e to the t, and some really unpleasant polynomial like t to the 9 minus 4t to the 3 plus 1. And I guess that should probably be a t in order to make my point, where it's like if I took the derivative of this, even if I did, it would still be hard to find out where it equaled 0. But I don't even need to do that, because, wait a second, hold on, I might need to do that. Yeah, if this had been like 2 to the t or something, that could never have a 0 derivative, but this thing always has a 0 derivative. So what you would do is you'd say, okay, this thing's always 0. This will have a 0 derivative at t equals 1. And what you would do is you would just make sure that, the derivative of this thing was not 0 at t equals 1, which I'm saying it's not, because it's going to be 9 minus 12 is negative 3 plus 1 is negative 2. Okay? So this thing is smooth everywhere. Okay? Get you a case of one where it would not be smooth everywhere. I've got an example. It's ready. It's r of t sine of pi over 2t. What else do I have? Natural log of t squared minus 2t plus 2. And what's the last one? T minus 1 squared. Yes. All right. Now the thing about this one is you don't want to just go and take all 3 derivatives and try to like simultaneously solve them for 0, because if this thing is going to be the 0 vector, then all 3 of them need to be 0, right? That's the only time where it's going to be not smooth. It's where all 3 are 0, or where one of them fails to exist. But you can check yourself. This is always positive. Okay, make sure of that. And it has just the right derivative so that it'll be 0 at the point I need it to be. So it's like no sense in going through this, because I know what this looks like. This has only one flat tangent, and that's at t equals 1. Okay, so my only candidate for a time when this function would not be smooth would be t equals 1. So I'm just going to test t equals 1. At t equals 1, I have, well, r prime is equal to, well, this would be pi over 2 cosine of pi over 2t. Well, t is 1. Okay, cosine of pi over 2 is 0. Okay, log of, okay, the derivative of log of a thing is 1 over that thing, maybe times its derivative. So 1 over t squared minus 2t plus 2. The derivative of the inside would be 2t minus 2. So 2 times 1 minus 2 over, that'll be a 1, that'll be a 1. So 1 minus 2 plus 2 is going to be 1 in the denominator. This is going to be 0 as well. And then over here, this will be 2 times 1 minus 1 to the first power. And then this is the 0 vector. So I would conclude that this function r of t is not smooth at t equals 1, but is smooth elsewhere. So you could say it's smooth for all t not equal to 1. You could say it's smooth on the interval from negative infinity up to 1, and the open interval, and then the open interval from 1 to infinity. That would be kind of wordy. It's just generally kind of easier to talk about where a function is not smooth. And you saw that last year, right? It's easier to talk about where a function is not continuous than to talk about all the places where it is. Okay, I think that's all I've got to say about differentiation of vector valued functions. Let's move on and do some integration. And the good news is this is going to work exactly like you expect, right? You're just going to take the integral of each component. And we actually did this last year in AP Calculus. When we were dealing with parametric functions, and we were just trying to find kind of the, position of the object at some later time or some earlier time, given a velocity function, that's what we did, was we kind of just integrated the x function and the y function separately, and we got ourselves a position vector. This year, we'll probably just do it all in one line, right? So now, starting off with just an antiderivative, right, an indefinite integral. we just saw earlier, I think I gave you good reason to believe that the derivative of a vector valued function is another vector valued function. So it would stand to reason that the antiderivative of a vector valued function would also be a vector valued function. I don't think I need to go in there and just in general talk about a theory of the antiderivative, right? I think it just makes sense. So what I'm going to do is I'm just going to start with an example. If r of t is equal to, maybe I'll write it as a vector like this. What was it? 1 over 1 plus t squared. Should have looked at more than just the first component. Cosecant squared of t and sine of 2t. All right, and then we want to know, find the antiderivative of r of t with respect to t. Okay. This is something that we're going to be able to do. We're just going to find the antiderivative of each of the components, and then that will be the antiderivative function. All right, well, what I'm going to do is I'm going to just say, well, this is separately 1 over 1 plus t squared cosecant squared of t and sine of 2 dt. And I'm just going to find an antiderivative for each of the components. Okay, antiderivative for 1 over 1 plus t squared? I don't know, maybe you forgot since last year. That's arctangent of t. Okay, but we also remember that when we're taking the antiderivative of a function, we're going to get a class of functions, a family of functions that are all separated by a constant. So I'm going to say plus c. But then I think about it, I'm going to have a plus c here and there. And they need not necessarily all be the exact same. So I'm going to call this c1. Okay, and then I'll have antiderivative for cosecant squared t. You might be like, I don't know about that. Well, we know that the derivative of cotangent is negative cosecant squared. So it stands to reason that the antiderivative of positive cosecant squared t would be negative cotangent of t. And those obscure trig derivatives, they are not going to be like a huge part of this course, but they are something I'm just trying to remind you about because I know, last year we didn't always 100% have all of those derivatives down. And I would like for you to. Plus c2. And then, okay, for sine, antiderivative for sine is going to be negative cosine. Leave the inside the same. But wait a second, if I took the derivative of this, I would incur a 2 on the outside, and I don't have a 2 there, so I'm going to need to maybe call it negative 1/2. And then there will be a c there. So this worked the exact same as it did before. This is no different. What I'm going to say is that you can also just say that this is, arctangent, negative cotangent, and negative 1/2 cosine 2t plus some vector c, where this vector c is an element of R3. If you wanted to write it like that, that would be just exactly the same. Okay, so that's just anti-differentiation working like we would expect. Okay, so now I'm going to do a definite integral. And, I think that you will also find that that works like you expect. But again, since it's been a while since we've done like that good old-fashioned derivatives and integrals calculus, might be good for us to practice. Oh, and then I've also got a motion problem for you that'll also be good practice for you to get back into the swing of calculus. So, suppose I've got g of t equaling cube root of t one over t minus 1 and 1 over over t plus 1. I was like, how am I going to integrate this from 0 to 1 if I've got a 1 over t minus 1? Makes sense. And e to the negative t. And we want to find the integral from 0 to 1 of g of t. All right, so what we're going to do is we're just going to find an antiderivative for each of the components, evaluate it between 0 and 1, have ourselves an answer. Okay, so I'll write this as t to the 1/3. I will write that as, well, I know that's not going to work with the power rule, so I'll just write it as 1 over t plus 1, and I'll say e to the negative. All right. Okay, antiderivative for t to the 1/3. I'm going to bump up the power by 1, so that would be t to the 4/3. Divide by the new power, it's 3/4. Let that run from 0 to 1. 1 over t plus 1, an antiderivative for that would be natural log of the absolute value of t plus 1. But since we're dealing with t's that are definitely greater than -1, an absolute value wouldn't do anything, so I'm just going to knock that there. And e to the negative t, well, that would be negative e to the negative t, as t runs from 0 to 1. And we can do that. We'll say that's 3/4 of 1 minus 3/4 of 0. This would be log of 2 minus log of 1. And we know that log of 1 is 0, so this is going to be natural log of 2. And then negative e to the negative t, well, negative e to the negative 1 is negative 1 over e, minus negative e to the negative 0 would be plus 1. Okay, so I think that was 1 minus 1 over e. Negative e to the negative 1 plus 1, yeah. Okay, and that's how we take a definite integral of a vector value function. We see it's just the same. If we were good at it before, we're still going to be good at it now. And if we weren't that good at it before, this is just an opportunity for us to, remediate that weakness. All right, and the last example I've got is a motion problem, and I'm going to just pause and copy the problem so you don't have to sit here and watch me copy for 2 minutes. All right, so an object starts from rest at the point 1, 2, 0 and moves with the acceleration a of t is the vector 0, 1, 2 for all t. It's a constant acceleration situation. And you're very familiar with constant acceleration situations if you've taken a physics class, right? That's where all the kinematic equations come from. And so the first kind of question I could ask you is, find its position at time t equals 2. It's like, okay, what we're going to need is we're going to have to bump up twice to get ourselves an r of t, and then we will plug in t equals 2. Right? So hopefully we've got 2 initial conditions. We do in the statement of the problem, and we will be able to find 2 orders of antiderivative for this. So v of t is going to be the antiderivative of a of t with respect to t. So this is going to be, okay, I can do this, 0t plus c, c1, 1t plus c, so c2, and 2t plus some other constant. But they told us in the problem that it starts from rest. Okay, so that means to me that v of 0 is equal to 0. As in the v0 vector. All right, and that means, okay, that when I plug in t equals 0, I need to be getting 0, 0, 0. So that means to me that c1, c2, and c3 all need to be 0. All right, so v is going to be equal to zero, yeah, 0, t, 2t. And then, hold on just a second. Oh yeah, and then I need r of t. So r of t is going to be equal to the antiderivative of v with respect to t, just like last year. And then I can do that. That will be 0t plus c1. It's a new c1. Here, I should call it c4. Since we're relatively new to this, that'll be 1/2 t squared plus c5. And 1t squared plus c6. Okay. They told me also that it started at the point 1, 2, 0. So I'm going to say that r of 0 is equal to 1, 2, 0. So that's telling me that C4 is 1, C5 is going to be 2, and C6 is going to be 0. C6 is 0. So I've got my function r of t ready. And that's going to be 1/2 t squared plus 2 and t squared plus 0. So that r of 2, which is the position at time t equals 2, is going to be 1, 4, 4. Okay, that's how we would just, find a later position. Really, it's just going to be, if we had v of t, we could have actually run a definite integral for that too. That's a strategy we have. I was focusing on the antiderivative here. All right, and then next, I might ask you about speed. You remember speed from AP Calculus. It was before we learned about parametric equations, it was the absolute value of velocity. And then when we realized that we could, let x and y do their own thing with respect to time, and that a lot of things would stay the same, we said it was the length of the velocity vector, which also is conveniently, we use the same symbol for the absolute value. So you know how to do this, you've done this before. It's just going to be the length of v of 2. Okay, so we are hoping to find the length of v of 2. Now I'm realizing that I don't have v of t written down here, but I'll tell you, it won't be too hard for me to remember. V of t is equal to 0t and 2t, because of it starting from rest, is going to be the length of the vector 0, plug in 2 for t, 0, 2, 4. Okay. And we can find that by taking the square root of the sum of the squares of the components. 0 squared plus 2 squared plus 4 squared. And in AP Calculus, we might have been, kind of satisfied to stop there, but I think we're kind of like, called to a higher standard, so we're going to probably say that that's 16 and 4 is 20. So we are kind of called to a higher standard to write this as a number, but I don't think that you're called to such a high standard that you're going to need to put this in simplified radical form and say that that's, 2 root 5, and I don't need that. Just need maybe something a little better than that. Okay, that's how we would find the speed. Okay, so there's just one more thing I've got kind of on my mind about this that I could ask you about, and that would be total distance traveled. Okay, total distance traveled, again, starting off with motion along a line, single variable calculus, we integrated the absolute value of velocity. We integrated speed. Okay, then in the parametric equations situation, we realized that the total distance traveled was the same as the arc length, and we did that by integrating the speed function, the square root of dx dt squared plus dy dt squared. And again, we were integrating the absolute value of velocity, which was the speed. So that's the exact same thing I'm going to do here. I'm going to integrate the absolute value of the velocity function. Now, what I'm going to need to do, because I need a number, right? This total distance traveled, this is a number, not a vector. So I need to be integrating a real valued function, not a vector valued function. So I need to go over here and say that the absolute value of v is going to be, well, it's going to be the square root of 0 squared plus, I guess I'll put that, 0 squared plus t squared plus 2t squared. And then when that happens, I'm going to have t squared and 4t squared is a total of 5t squared. When I take that, well, actually, maybe you can see where I'm going here. That's going to be equal to the integral from 0 to 2 of the absolute value of v of t dt. And this is a real valued function, this absolute value thing, right? It just depends on t. It's just a number. And so this is going to be, what I can do is I can say that the square root of 5 is a factor I can pull out to 2. Now, the square root of t squared, really that's the absolute value of t, right? But since, again, we're only looking at places where t is not negative, that absolute value wouldn't do anything. So it's just going to be a t dt. Okay. And this is the type of integral we're very good at, right? We can bump up the power by 1, divide by the new power. And that's going to be square root of 5 times 1/2 t to the 2 as t runs from 0 up to 2. So this will be the square root of 5 times half of 4 is 2 minus 0, and that's 2 times the square root of 5. And I think that's all I've got to tell you about derivatives and integrals of vector valued functions. Now, if you found this video helpful, I am going to go ahead and ask that you consider giving it a like. But that's all I got for you. Thank you.